Hello everyone and welcome to video number 1 in getting started with FEM 4.2 course. In this video we are going to have introduction about numerical methods and finite element analysis to be ready to start the FEM 4.2 software. Let's start. We are going to start by this sentence: analytical and numerical methods, pros and cons. We can put it in a question format. Do we need numerical methods? What is the difference between analytical and numerical methods? So we are going to answer now. Regarding the analytical one, often provide the exact solution because we solve the problem manually or simple code using M code, for example. But there are some limitations limited to simple geometry and source distribution. The problem domain is often simplified to achieve a solution. In most cases, we cannot encounter saturation or nonlinear behavior, somehow complex analysis in the 3D, possible mistakes for manual solutions. For numerical one, nowadays it is possible to solve 3D, nonlinear, transient, time-step model of electrical machines coupled to a complex mechanical load and more. Also encounter nonlinearity and saturation effects. But there are some limitations for the numerical techniques. Solution might take many hours and some cases take some days. There is a band of error because that one depends how you are going to feed the problem or enter the data to your problem. So we have here in both cases pros and cons, but definitely numerical solutions find another way to solve complex problem, which is important to find some physical features in our models. Someone can ask this question: what is a numerical analysis? So numerical analysis is modeling, error, accuracy, precision and rounding, Taylor series and truncation error, Maclaurin series, finite difference techniques, bracketing techniques, roots of polynomials, Gauss's elimination, matrix calculation, Euler's Newton-Raphson method, Range-Kotte methods, but we don't know anything about this stuff. If you like to know more about that one, visit this reference, Stephen Chabra one and his team, Numerical Analysis, Numerical Methods for Engineers. Here I'm going to present for you one of the numerical techniques, iterative solution of two-dimensional Laplace's equation by finite difference method. So using Laplace's equation, second derivative of voltage with respect to the x direction plus second derivative of the voltage with respect to the y direction equals 0. So I'm going to use Taylor series here, and we are going to make a long division. If we look here for a general point C, so the voltage at point C, VC, depends on the voltage on point number 1, 2, 3, and 4. If they are equidistant, we are going to have the voltage at C point equals quarter V1 plus V2 plus V3 plus V4. We are going to make another iteration, a third iteration, fourth iteration, until we reach minimum error. Still, we didn't understand that one. We are going to see that one by an application. We are going to apply the finite difference method for this Trough test problem. So we have a conductor with 4 edges. One of them is 100 volt and the other 3 conductors are 0 volts. So we have 12 points. They are distributed equally from point number 1 up to point number 12. So how we are going to start the problem? We are going to put an initial estimate for all the points 0 volts. For a point like number 1, so we are going to have 0 plus 0 plus V2 plus V5 over 4. For point number 2, we have V1 plus 0 plus V3 plus V6 over 4. For point number 3, V2 plus 0 plus V4 plus V7 over 4. For point number 4, we have 100 plus V8 plus V3 plus 0 over 4. And so on for all the points. For iteration number 1, points 1, 2, 3, 5, 6, 7, 9, 10, 11. All of them are 0 volt, still 0 volt. But point number 4 would be 100 plus 0 plus 0 plus 0 over 4 gives you 25 volt. And the same for point number 8 and point number 12. We are going for second iteration based on this column. So we are going to calculate based on the first iteration. So what is the second iteration? Still point number 1, 0. Still point number 2, 0. But point number 3 depends on point number 4 in the previous case. So that one will be 0 plus 25 plus 0 plus 0 over 4. So that one gives you something like 6.25 or 6.3. For point number 4, it will be 0 plus 100 plus V V8 from the previous case, which is 25 volt plus 0 over 4. So that one will be 31.3 now. And now point number 8 will be V4 from the previous case plus 100 plus V12 from the previous case. So that one will be 150 over 4, give you something like 37.5 volts. And the same for point number 12. So points 9, 10, 11, 12 are identical to points 1, 2, 3, 4. Going for the third iteration, you are going to find there is an improvement in the voltage here. So point number 2 now has a voltage. Point number 1 is still 0, but point number 4 is improved to 35.9, and point number 8 will be 42.2. So moving more until we have accepted error. So going up to 7th iteration, we have now point number 1, 1.7 volts, point number 2, 6 volts, and point number 3, 16.5 volt, point number 4 will be 41.3 volts, and point number 8 will be 50.3 volts. We need to answer these two questions. What about accuracy? How to improve the solution? This is what we are going to do using the finite element software. We're going to apply the same problem using FEM and check for these values. So now we achieved with this iteration, 7 iterations, 50.3 volts. What will be the answer if we're going to use the FEM software, for example? So now we know an idea about the solution, what should be. And then we're going to find the best values using the finite element software. Before we delve more in the FEM software and how to build the model, let me show you what is the benefits of the finite element analysis results. We have this shape here. We have 6 sides. 2 of them is 100 volt and the other 4 is 0 volt. We're going to build that one, for example, using FEM software to see how the electric field is distributed through these points. So let's look. For the electric field for this point is 1 kilovolt per centimeter. What will be the case if I make that one is rounded, is not a sharp corner? Let's look. So now the voltage is distributed as we can see here, and the electric field at this point is 0.22 kilovolt per centimeter, and this point is 0.3 kilovolt per centimeter. And the average electric field per volume is dropped from 0.19 kilovolt per centimeter to 0.16 kilovolt per centimeter. So what is the advantage? What is the benefits? So the manufacturer for electric panels nowadays using bus bar without sharp corners to avoid the high stress, and they are going to use the round corners here to lower the electric field stress for these bus bars. And the finite element analysis for something like that one helped us to see the pattern or how the electric field is distributed through this figure. A common question from our students: why the geometry of cables is cylindrical instead of square? So we need to answer this question. So let's take a cable with 1 volt, take it per unit, PVC material, relative permittivity is 3. I'm going to take the conductor is 10 millimeter radius and the insulator is another 10 millimeter, or from the center point will be 20 millimeter in the horizontal line. So let's look for the cylindrical one. We have 10 millimeter and another 10 millimeter here. So that one all in all will be 20 millimeter. And if we look for the voltage distribution, we have from 0 up to 10 millimeter, we have 1 volt, which is the conductor. And then the voltage is going to drop from 1 up to 0 because that one is the outer frame of the cable. So that one will be grounded. So that one is dropped from 1 volt up to 0 volt, which is anticipated. So let's look for the square cable. We have the same blue line here, which is identical to this one. And we have another line here, which is the red line. So that one is 10 and that one is 10. So definitely that one will be 10 root 2. And that one will be 20 root 2. If that one is 20 and that one is 20, that one will be 20 root 2. So we don't have here one radius for the square cable. So what will be the voltage distribution? Let's look. For the blue one, we're going to have 1 volt until drop to 0 volt after 20 millimeter as expected, like the cylindrical one. But for the red line, that one will be 1 volt up to this point, which is 10 root 2, and then it's going to drop up to this point, 0 volt. So we have more voltage for this red line now. What is the problem? No problem for the voltage, but we're going to look for the electric field. What about the electric field? For the cylindrical cable, we have a contour line, the blue one. So we have maximum electric field, something like 140 volt per meter, and minimum one, something like 70 volt per meter, and that one is expected. What about the square cable? We have a blue line and the red line. For the blue line, something should be close to what we saw here in the cylindrical one, but for the red line, we don't know what will be the results. But remember this point at 10 millimeter, that one is at 10 root 2. That one is 20, that one is 20 root 2. Let's look. For the blue line, we have 0 inside the cable for both cases, and that one is expected. There is no electric field for the copper conductor. So from 10 to 20, we have here something like 100 volt per meter, which is nice. We have lower compared to that one, but let's look for the red line. At this point exactly, we have a abrupt change for the electric field, increases up to 600 volt per meter. And that one is a high stress for the cable insulator. So this is why we prefer the normal distribution for the electric field, the radial one, rather than a square cable makes more stress for these sharp corners. What will I watch in video number 2? Video number 2, we are going to cover why FEM 4.2. What are the capabilities, limitations, and applications? See you in the next video.